Okay, so this extends the method of Frobenius to finding power series solutions to differential equations around singular points. So remember, a singular point is where if you divide through by that coefficient on the highest ordered differential term in the differential equation, the singular point is anything that makes those other coefficients equal to 0 under the denominator. Usually is what we get. It makes, in particular, when the functions fail to be analytic, for our purposes, it's going to be discontinuities where we have zeros in the denominator. So to that end, let's see if we can do an example. Let's look at number 22 on page 239. That gives us x squared y double prime minus 3 plus 2x times y prime. I'm looking at the wrong one, sorry. It's plus x times y prime plus x squared minus 4y, or 4/9 times y equals 0. Notice in this case, if we move that x squared, divide through by the x squared, we really do get a singular point at 0. In this particular case, it'll be a regular singular point. Everything that we're going to deal with as far as finding solutions will be regular singular points. We're never going to find a power series solution around an irregular singular point anyway. So everything will be regular singular points. So the idea here is to try to handle that singularity by adding an extra piece to what looks like the power series method. So we use that plus r piece up in the exponent. It gives us a little bit more playroom as opposed to trying to just use a normal power series. It gives us a little bit more playroom using different powers. We can get negative powers here. Because when we think about negative powers, we would have those singularity ideas. We'd have asymptotes, things happening. Maybe fractional exponents where we might get cusps or vertical tangents. That r term in that exponent gives us a little bit more play in being able to find a solution that looks like a power series. So we're going to use this particular form, and again we're going to do this using GeoGebra to help us out. So let's flip over to GeoGebra. Let's see if we can get a new window here. Get a nice fresh start. Turns out that GeoGebra, you can define these in terms of functions. You'll need to use, if you define these in terms of functions, you'll need to use an x and an r in your definition, so you'll have a function of two variables. Turns out that GeoGebra usually takes a long time to do the computations if you do that, so we're going to just skip that step. So the first thing we're going to type in here is just get our power series like representation, the same way we did it before, but we're going to put an n plus r in the exponent rather than just an n. So this is exactly the same type of command we used before. We'll have the sum of that c of n x to the n plus r, and we'll go from 0 to 15. Again, we don't need to use the sequence part like I did before. We just don't need to do that. So now we need to plug that into the left-hand side of our differential equation. So notice again, this is a function of two variables. It has that x to the r, the x and the r in it. So when I take the derivatives, I want the derivatives with respect to x, so we'll actually have to use the derivative command here. So we want to take the derivative of that expression that's in number 1. The variable is x that we want to differentiate with respect to. Now we're plugging it into y double prime, so we want the second derivative. Then we have plus x times the derivative of number 1 with respect to x, and take the first derivative. And then plus x squared minus 4/9, and we want to multiply that by number 1. Might take it a second to be able to do this, so we'll be patient and let it take care of it. I mean, we got a lot of terms there. It's got to do a lot of derivatives. There we go. So this is what the derivative looks like. The next thing is that I want to try to be able, the whole point of this is to try to be able to pick off those coefficients and get at recurrence relations. Because again, we've plugged this into that left-hand side of that differential equation. The right-hand side is 0. So we want to get that recurrence relation where all of these constants are equal to 0. To do that, I really want to be able to factor off an x to the r. That's the idea. It's a little harder to do that on GeoGebra, so we're going to force it. So the next thing we're going to do is type in simplify. We're going to simplify that second expression. What that's going to do is it should pop out each of those x to the r's as separate terms as we go across. Again, might take it a second because it's a long polynomial, so it takes a little effort for GeoGebra to do it. So we'll be patient. There it is. So notice that in each of those terms, it's popped off at next to the r. So to get an essence of being able to factor out that x to the r, what we're going to do is we're just going to replace it with a 1. So in that expression in number 3, we're going to change it from x to the expression x to the r. We're going to change it to a 1. And so that's going to have the effect of removing all of those x to the r's. Again, be patient. Give it a second to do it. A little longer in this case. It actually has to do some substitutions and do some simplifying. So again, we'll be patient. There, we're done. Okay, so now we want to figure out what values of r have any hope of making this work. So the way we're going to do that now is we're looking for the equation on the lowest degree term that we have in this particular case, or what would be on the x to the r term, if you will. So to do that, we're going to take, in this particular expression in number 4, we're going to substitute in 0 for r. Because this will give us what would look like the constant term on what was left after we popped out the x to the r term if we were actually factoring out and doing this by hand. Again, takes a little bit. There we go. Whoops. I'm sorry, I did the wrong thing. I put in 0 for r instead of 0 for x. Let's go back up here. I apologize. Let's delete out that one. I want to substitute in number 4. I want to get the constant term. I put in the wrong thing. I apologize. I want to put 0 in for x. Should come out something relatively simple. There it is. Okay. So we get r squared c naught, and we get a minus 4/9 c naught. We want to solve this for r. So we'll do solve. I'm going to solve number 5 equals 0, and we want to solve it for r. And there are our two solutions for r. So again, when we set this equal to 0 and ignore the c0, because there's always going to be a c0 term in it. So we're going to ignore that c0 part. The equation that we would get is what's referred to as the indicial equation. We talked about that in class. So our indicial equation here would be r squared minus 4/9 equals 0. So the roots that we have of that are the roots of our indicial equation are telling us what the two possibilities are for us for finding solutions to the differential equation. All right, so what we want to do is take these now, plug them back up into our expression that we came up with in number 4 to get the recurrence relation to figure out what the constants have to be in those cases. So let's go and we want to substitute in number 4. We want to replace the r with, let's do the negative 2/3 to start with. Again, it takes a little, there we go. Okay, so now this is a polynomial. Remember that it might be the case that this expression that we had up here in number 4 might have had an x in the denominator, so you might have needed to clear out that x. We saw examples of that in class. You might have to multiply it by x first before you do these other steps, so make sure you keep that in mind. All right, so here is our polynomial that we get after plugging in negative 2/3 for r. So we want the coefficients of that, and that's what, and that's what will give us our recurrence relation. And again, one of the reasons why we're not defining each of these as functions and having to go back and refer to things by line numbers is notice how long it's taking with this. It takes even longer if you define it as functions. At least it has for me on GeoGebra. If you have better luck with it with defining it functions, by all means, go ahead and do it. But this takes a while. It's still working. There we go. So here are our coefficients that came out. There we go. Now we can stop this. All right, so now we've got these where we can get our... That's weird. I don't know why it didn't. Let me go back, because I thought I replaced the R with 0. Let me go back. Or with the R with the negative 2/3. Oh, I know what I did. Let's delete number 8. I apologize. I substituted the number in the wrong spot. There we go. I want to substitute number 7 here. I apologize. Okay. Number 7, I want to replace the R with the negative 2/3. Oh, no. No. That's not what I wanted to do. I've already got it substituted in there. What I wanted to do, I did the coefficients of the wrong polynomial. Oh, goodness. Sorry about that. Number 7 is the coefficients I want. All right, here we go. That's much better. So notice in this one, we've got a recurrence relation that pops up pretty quickly here. That we've got this, notice we've got negative C1 over 3 would have to be 0, which tells us C1 has to be 0. That in turn makes this one equal to 0. This one will be 0. This one will be 0. Because if C1 is 0, C3 has to be 0. If C3 is 0, C5 has to be 0. And so on down the line. So all the odd ones here are going to be 0. So the only recurrence relations we really need are the even ones. So we have the 4C2 plus 3Z0 over 3. So 4C2 plus C30 would have to be 0. I can ignore the over 3 part because I could just multiply it to the other side. And then 0 times the 3 will be 0. Flip back over again. We would have 3C2 plus 34C4 is 0. Flip back over. We have 3C4 plus 84C6 is 0. And so on. At this point, this will give us 4 terms, so we might as well stop. This one tells us that C2 is 3/4 C0. This one tells us C4 is 3/32 C2, which would give us 9 over 96. Nope, not 96, 128. C0. And then C6 will be 3 over 84 C4. So it'll give us, 27 over, actually 3 will go into that. 9 over 3 goes into 84, what, 28 times? So 28 times our 128 gives us 3584. So one of our solutions are y1. Now we've got a recurrence relation. We'll ignore the C0s because we're literally looking just for 2 linearly independent solutions because we know we can multiply them by constants to get our general solution. So let's just ignore the C0. One of our solutions will be, well, this is referring to a 1 plus a 3/4 x squared plus a 9 over 128 x to the 4th plus a 9 over 3584 x to the 6th, and so on. However, remember, this corresponded to plugging in negative 2/3 for r. remember way back at the beginning we said that plugging in that 1 for x to the r had the effect of factoring out the x to the r. Out in front here, there's going to be an x to the negative 2/3. So that gives us one of our linearly independent solutions. To find the other, you do the same process, except that we go back over here, and instead of substituting in negative 2/3 into the number 4, we're going to put in positive 2/3 into number 4. So we'll do substitute into number 4. We want to replace the r with 2/3. Again, we'll probably take a minute. Okay, and then we want the coefficients for this. So coefficients of number 9. There they are. And let's scroll to the right. Notice again, we get a C1 is 0, that makes C3 0, that makes C5 0, and so on down the line. So again, all we really have are the even terms. We can ignore the denominators again, because if we set each of these to 0, we can multiply over by the denominators. So let's do that. So if we go back over, we've got, looks like we had a 20 C2 plus C0, 3C0 is 0. We have a 3C2 plus 64C4 equals 0. That's a C4. We have a 3C4 plus 132C6 equals 0. And so on. So the first one gives us C2 is 3/20 C0. This one gives us C4 is 3/64 C0, which would give us 9 over what? 1280 C0. C6 will be 3 over 132 C. Oh, these are negative, aren't they? This is negative. This one will be also. I'll go C2. This will be negative, which makes that one positive. This one will be negative. I can write these things. This next one will be negative. Let's see, 132. Okay, so 3 goes into 132. That gives us 44 times 1280. So we'll get a 9 over 56, 320, C0, and so on. This will give us 4 terms. So again, we can write our second linearly independent solution. We'll have a 1 minus a 3/20 x squared plus a 9 over 1280 x to the 4th minus, this should have been a minus here, 9 over 56, 320 x to the 6th, and so on. And then again, remember we plugged in 2/3 for r, so out in front we would have factored out an x to the 2/3. So that would be our second linearly independent solution. So this is how we apply the method of Frobenius to helping us solve differential equations using power series-like solutions when we have singular points.